Hello, I'm Dr. Harper. This video is an Operations Management Inventory-2 lecture, which contains stochastic models. Let's bring up the notes. Now in the notes, we start with Inventory Management 1. I covered the basics of the input-output model where you acquire items from the supplier to increase inventory, distribute items to the customer, which will decrease inventory. I covered the inventory policy, which contains the two fundamental questions of inventory theory: how much to order, the lot sizing question, or the quantity order from the supplier, and when to order, the lot timing question, or when to order items from the supplier. And also in inventory management number 1, I covered the basics of constant demand. We had the fundamental relationships of when to order and how much to order, the reorder point of when to order, and the economic order quantity of how much to order, and the two review systems of the continuous review system and the periodic review system. And I covered the definitions of the T, the inventory period, the lot size Q, the demand rate D, which is a constant demand rate. ROP were the lead time, safety stock, ordering cost, carrying cost, economic order quantity, etc. But in this video, we're moving from constant demand to stochastic demand, where the demand now is a random variable, follows a normal distribution in this development, and in the normal distribution, it changes, and it's more realistic on how inventory management is controlled and managed. We'll have first with when to order the statistical safety stock, where the safety stock then is a combination of probability, variability of the demand rate and the lead time, single period EOQ, and then finally the base stock level, which is the periodic review system. I will end with, I don't develop, but I end with alluding to stochastic demand can also have stochastic lead time, and the lead time upstream to the supplier can be stochastic. The demand downstream to the customer can be stochastic, or they both can be stochastic, and that there's where you have realistic inventory management. So, an overview: if you remember, in economic order quantity models, we had stochastic demand with a single period and multiple periods, and I'll do both of these in this video. The following represents an introduction to the stochastic inventory theory. The stochastic demand initially follows a normal distribution. I'll start with a continuous review with a zero safety stock. It's a good place to start because with zero safety stock, then in the continuous review system, the constant demand, stochastic demand really is the same. Changes happen when the safety stock is not zero. Then you get into, in the continuous review, you get into statistical safety stock, and the statistical safety stock has to do with the stockout level, and that stockout level is a probability introduced into your inventory policy. I first have the derivations, and then I apply it, and then I go to the single EOQ model, then I go to stochastic demand session on how to calculate the mean and variance, and then the periodic review of the base stock level, and then I end with some extensions. So let's do it. Let's get into it. First of all, continuous review system with a zero safety stock. Well, here's the deterministic demand or constant demand rate. Let's suppose it's 539 a week. So we have 539 demand items every week that we have to satisfy. The stochastic demand, however, is the demand rate, which follows a normal distribution with a mean of mu of D and a variance of sigma squared of D, where the mean is 539 a week. So I'm picking the mean to be the same as the demand rate, but that's the mean now. It can vary around 539. The variance around that is 6724, and the standard deviation is 82. Note, for stochastic demand, D follows the normal distribution of mu and sigma squared, where mu is the mean of the demand rate, the expectation of the demand, and sigma squared is the variance of the demand rate, the variance of D. The standard deviation of D, sigma of D, is the square root of the variance of D. Just a reminder, a review on the definitions. Now, when you have a stochastic demand here and the demand follows a normal distribution, you see here the mean is 539, but the demand, which is the random variable, can vary around that mean of 539. This d of alpha here is a variate. And so I want to distinguish between a variable, which represents something that varies, and a variate, which it doesn't vary. It is one value of a variable, which is defined. And notice the definition is a subscript alpha, and that alpha is the probability in the tail, the upper tail of the distribution. And this alpha, as it turns out, is going to be the stockout level. 1 minus alpha is the service level, and there's where probability comes into inventory theory. But I'll show you how to figure it. Okay, we can transform the d to a z value by subtracting the mean and dividing by the standard deviation. This is a normal z transformation, where now the random variable, the normally distributed random variable d, can be replaced with the standard normal random variable z. Again, the variate can be placed with z, and the mean now is going to be 0, and the variance is 1. Now, the reason we transform it to the z is because the z then has tables, it has algorithms, it has functions that can be used to approximate the probabilities very quickly and very easily, and we'll be using Excel. Okay, so let's get some examples. Suppose the lead time is 0.2 weeks and the inventory period is 1.5 weeks with 0 safety stock. The safety stock for the deterministic demand or the deterministic model is 0, and for the stochastic demand it's also 0. So I just comparing these here. Notice here are the equations. The ROP is the demand times lead time plus safety stock. We saw that in Inventory Management 1. But over here, stochastic demand, I replace the D, the demand rate, with the mean of the D. I replace the safety stock, which is just a value, with the statistical safety stock, which is dependent on alpha, the stockout level. Well, in this case, the safety stock is both 0. And here I have the demand rate. Here I have the mean of the demand rate. The lead time is the same. And so notice in this case, the ROP is the same. In this case, for the the inventory period of 1.5 weeks here, my demand rate is 539. My mean of my demand is 539. And so the inventory policies are really the same. And that's why I'm starting with 0 safety stock, because if the safety stock is 0, then essentially what's happening is your inventory policies are going to be the same. There's no difference. Okay, now what happens when the safety stock is not 0? Whenever you have a stockout level with a probability which is greater than 0. Okay, now first I'm going to derive it, and the derivations are not going to be important in the classroom, but I go through them quickly to see where it comes from. So you won't be using it. It's just knowledge to know how to use what we're going to calculate. The stochastic demand follows a normal distribution, and the stochastic demand during a lead time. In other words, you have your demand, but then during a specific lead time now, the lead time times the mean, the lead time times the variance. So that mean, the new mean and the new variance, is the mean and variance of the demand during the lead time. And we'll be using this here in just a second. Now the probability of stockout is alpha. The probability that demand during lead time exceeds ROP, where ROP is this, and the probability that demand exceeds ROP during lead time is stockout. So the probability of stockout is once you have ROP, that during that lead time, if the actual demand during this lead time exceeds your ROP, then that's going to be stockout. So let's take that concept. From the probability of stockout, the probability is that the demand during lead time is greater than ROP. Because if during this lead time, if demand is more than ROP, we've ran out of inventory. We do not have inventory to satisfy that demand. When you have unmet demand, that's the definition of stockout. So this describes stockout. I'll let you think about that. That's important. Now in ROP, I can replace the equation. So I replace the equation here for ROP. And now I have a normally distributed random variable on the left-hand side. I have constants on the right-hand side with a mean, which is constant, lead time, which is constant, and my safety stock then is going to be a function of constants here in just a second, which I'll show you. Now, since from the z equals the demand times lead time minus the mean, which that's the mean, remember that's the mean of the distribution, divided by the square root of the variance of the distribution, from the z transformation of the normal distribution. So the z, that's the z transformation, but I'll do applying the transformation to both sides. What I mean by that, applying this transformation to the left-hand side, then this d becomes a z, and there it is. But if I perform this transformation on the right-hand side, well, first of all, the lead time and the mean cancel out, and what I'm going to be having then is just the safety stock divided by the standard deviation of the demand during lead time. So now I have this expression. I combine this with the basic probability of z greater than z of alpha is alpha. Okay, so then I can compare these. So if these are both z, then z of alpha is going to equal this right here. So therefore my z of alpha is going to equal this. I can solve then, I didn't put it in here, but if z of alpha equals this, I can solve for the safety stock of alpha, and I get this expression. It's z of alpha times the square root of the lead time times the standard deviation of the demand during lead time, or the demand. And so this right here is your standard deviation of the demand during lead time. And so now you have your expression for the safety stock. Summarizing, the ROP is given to be this, the mean times lead time plus safety stock. But the safety stock we've derived to be this. So there's your ROP equation. Now this derivation is not really important. I went through it quickly. I could have gone through it slower, but you can go through the algebra if you want. But this is where this expression comes from. In other words, we said this expression came from my probability of stockout, and that's why alpha is the stockout level. 1 minus alpha is the service level. The sigma d is the standard deviation up here. It's the standard deviation during your lead time. It came from the variance. And here's your square root of lead time, because that came from the stochastic demand during the lead time. So it all came from a derivation. So it isn't just random. It isn't pulled out of the air. It is derived. So let's apply it. Okay, so let's let our lead time be 0.2 weeks. Our inventory period is 1.5 weeks. Our safety stock is 0. I repeat that here. Now, consider the statistical safety stock which is greater than 0. Okay, the reorder point here is given by the mean times the lead time plus safety stock SS of alpha. The statistical safety stock is given by this expression, which we derived up here. Where's it at? Here it is. We just derived it. There's more safety stock. So I'm copying that down here. And there it is. Okay, I can put these together for my ROP. So the mean times the lead time, which is this, I substitute my safety stock in for that safety stock, and there's my expression for my ROP. Let's do the calculations. So my demand follows a normal distribution with a mean of 539. That's going to be the mean. The standard deviation is 62.74. My inventory period is 1.5 weeks. My lead time is 0.2 weeks. My stockout level is given to be 10%. Okay, so therefore my service level is 90%. Both of these have to sum to 1. So my z of alpha, which is z of 0.10%, that 10% is in the tail of the distribution, turns out to be approximately 1.282. Well, we're going to get these values from Excel. And the Excel function is here given to be 0.09 normal standard inverse the inverse because we're giving the z value and then we're calculating the random variate. Okay, so the inverse will give you the random variate. The distribution from a variate will give you the cumulative probability. Well, let me just illustrate this real quick with Excel. Let me bring up Excel. And here, let's enlarge this a little bit so you can see it. Bring this down here. Bring this up so we can actually, here we go. So essentially all I'm going to be doing here, I'll put it right here, that's going to equal the normal, standard, inverse. And that's what that means. It's the inverse of the function, 0.9 pressure return, and you get 1.281552. It's an algorithm which approximates it. So we can come up here and oops, I just clicked out of it. We can come up here and reduce the significant figures, and it's approximately 1.282, and there's where the 1.282 came in. Now remember, I'm just representing it. That's what this squiggly equal means, approximately 1.282, because it's really something much larger. That's the number. Well, it's not the exact number. It's an approximate number. It's rounded to 1, 2, whatever significant figures those are. That's why I say in Excel, use Excel because you use all the significant values to calculate the values. I mean, all the significant numbers in your number. In other words, don't round during calculations. Use all the numbers, and that's why we use Excel. Okay, let's go on. So my ROP is given by this, and here's my safety stock. ROP, I bring down. Here we go. I bring down the 539. 539 done by 0.2 is going to be my lead time. My Z of 1.282, I pull that down here. My sigma, I have the variance. So I take the square root of the variance, which is the same as the standard deviation. So sigma is the same as the square root of sigma squared, times the square root of the lead time, again, which is 0.2. And notice in the ROP, the lead time is a function of the ROP. The inventory period is not. Okay, over here on the lot size Q, we have the inventory period of 1.5. We have 809. And so we add this together, we have 1.55, we have 809, and there's our inventory policy of our ROP is 155,809. Now I want to compare this before we move on with the deterministic. Let's come back up here to deterministic. Notice my deterministic was 108,809. Okay, so let me just copy this and bring this down here where we were. And there we are. And so let's paste this. Whoops, let me bring down, there we go. Now paste it. And notice that it's just 108,809. The 809 does not change. It's the same as this is a zero safety stock. Now the zero safety stock certainly is going to increase, but increases because of your stockout level. So the stockout level, when you increase the stockout level, it's going to start increasing your safety stock to 108 to 155. But then what is it a function of? I want to emphasize this, and this is a takeaway. Well, it's a function of your ROP. Your safety stock is a function of your alpha, your Z of alpha, your sigma, and your lead time. Okay, so as the lead time increases, your ROP increases. As the variability of your demand increases, your lead time increases, your ROP increases. And as Z of alpha increases, your ROP increases. But wait a minute. Alpha is the stockout level. So if alpha gets larger, what happens to Z of alpha? Does it get bigger or does it get smaller? Okay, let's back up. Let's go back up to the Z function up here. Here it is. If this alpha gets larger, then Z of alpha gets smaller. Okay, then in order for the ROP to get larger, Z has to get larger. In order for the Z of alpha, the Z variant, to get larger, alpha must be smaller. But alpha is the stockout level. So lower probabilities of stockout will increase your ROP. Hopefully that makes sense. Because if you have larger and larger ROP, the probability of running out of inventory during that lead time gets lower because you have more inventory. As the inventory increases, the probability decreases of running out. Well, 1 minus alpha is the service level. So we could say down here, comparing this further, that it is as the service level increases, ROP increases, because the service level is inversely related to the stockout level. So ROP will increase when the lead time increases, when the variability of your demand increases, or the volatility of your demand increases, and when your service level increases or your stockout level decreases. Now, the reason that's important, I'm trying to emphasize this, is because notice it is not a function of the inventory period, T. T is not a function in the ROP. In other words, suppose the inventory period increases, you're going to increase your lot size. But what if your lead time increases? Do you increase your lot size? No. Your lot size still remains the same. The ROP increases. So if your lead time increases, your lot size remains the same, but the ROP increases. You order it sooner. You don't order more. If your demand variability increases, if your demand becomes more volatile, oh, I have more uncertainty in my demand, what do? I want to order more. No. You order the same amount. You order the same amount earlier. So it's the time that adjusts for volatility, not ordering more. You order the same amount earlier. It's the time in this development. What about the stockout level and service level? I want to increase service level. Well, usually the initial reaction is, oh, I want to have a better service level, so I will order more. No, order it sooner. If you increase your service level, the probability of service, you increase that, order the same amount, just order it earlier. And that usually is the opposite of what a lot of people will do. Oh, if volatility increases, order more so we can satisfy it. If our service level increase, we want to service our customers better. We want to lower the probability of stockout, increase the probability of service, order more. And what happens is that's a disjoint. The error increases, inventory increases, and you have something called the bullwhip effect within your supply chain. So you don't do that. What you do is order the same amount earlier. It takes discipline, but if you do it, then it works. And you lower cost, increase efficiency. So there's a takeaway. Let's continue on. Let's go to the single period. Now, a single period says we're just looking at one inventory period, not multiple periods. Because before that was the continuous review. We review it every inventory period. Now we have a single period. So now we have stochastic demand during a single period. Okay, and there it is. Now, in order to do this, you say, okay, I'm ordering this one time. If I order it one time, well, I could order too much, or I could order too little. If I order too much, then I'm going to have something called a long cost, or the cost of inventory remaining after the inventory period is over. In other words, your lot size is too large. Your demand is less than your lot size. That's called long cost. Your short cost is your demand is not satisfied during a lead time. During your inventory period, during that single period. In other words, your lot size is too small. You didn't order enough. and the demand is greater than your lot size. Well, if the lot size is too small, if demand is greater, then you have demand unmet. That's really part of your cost of your stockout level. Stockout. Okay, well, how do we determine our Q? By looking at the cost of stockout. Well, we determine the lot size Q by saying, okay, I'm going to take the cost of stockout times the probability of my demand greater than my lot size Q, because that represents stockout. Q is my order lot size. If my demand is greater than that I don't have enough inventory to meet my demand, so that's stockout, unmet demand. Long cost is when your demand is less than your lot size. I've ordered too much. My demand is here, my lot size is up here. So that's long cost. Okay, so I can rearrange these where the short cost equals the long cost, and then collect terms. And here I have an expression for my stockout level, the probability of demand greater being the Q is my stockout level. That's the same as my long cost divided by the long cost plus the short cost. So I can define my stockout level by that ratio. Interesting. So when I define my costs will determine my stockout level, which will determine my EOQ. So the probability is the same as the Z, which is Q minus alpha over sigma from the normal distribution, like we did before, comparing with our Z of alpha with our variate. We equate our Z of alpha variate with this expression here, solve for Q, and we have an expression for Q now. And that Q minimizes cost, so we call that Q EOQ. It's the mean of the distribution plus the Z of alpha, where alpha is a stockout level, and that alpha is derived by that expression right there, times my the standard deviation of the demand. Calculations. So here we have our demand. Again, suppose our demand is a normally distributed random variable with a mean of 539, variance of 67.24. Given the long cost is $3 and the short cost is $27. Now right here, let me just mention. Notice how much more the short cost is than the long cost. And this is traditional. This is conventional. This is usually what happens. In other words, your short cost, which is your stockout cost, usually is much greater than long cost. In other words, if you order too much, the cost of carrying too much inventory is much smaller than the cost of running out of inventory and having lost sales, lost customer, lost demand, lost brand. And maybe those customers don't come back and you have future lost sales, even when you do have inventory. And so usually this is the case. Okay, and notice this is almost an order of magnitude more. So let's go on with the calculations. I calculate my stockout level, which is 3 over 3 plus 27 turns out to be 10%. Thus the service level is 90%. Okay, I made it turn out that way because now my Z is 1.282 from the standard normal inverse function in Excel. I take the equation, I plug in the numbers. Here's the 539 for mean, 1.282 approximate for Z of alpha of 10%, and the square root of this is the standard deviation. So now I order 644. And so that's the equation. That's how you derive it. I mean, that's how you get your lot size. Now notice how next is the stochastic demand session. I put this session in the lecture because notice you say, well, if I know what my mean is, if I know these numbers, I can calculate it. Well, the practical side of it then is, how do you get the numbers? How do you get the 539? How do you get the 6724? How do you get these values here from your distribution? We're assuming that we have this. When we start measuring it from our measurements and our data, from the data, how do we come up with the mean and variance and standard deviation? That's what this session is about. For example, and I do it a number of ways, and I'll do this in more detail in the homework, and I'll show you how to do it in the homework. The weekly demand for an inventory item has been collected for over 100 weeks. Now I picked 100 weeks because it's just convenient. A portion of the data is presented in the table. Here's table 1. So week 1 through 5, 96 through 100, there's our demand. And so I keep measuring. And so suppose you had all of the data. That's nice. If you did, in Excel, the mean, variance, standard deviation, max, min were determined using these formulas. And I give you the formulas. Equals the average. And the data here is you just include all the data. You lift and drag and put all the data in there. And there's 539. The variance, and I'm using the population variance. P is population variance. The standard deviation population, the min data, the max data, and the range will be the difference here. So all I'm doing here is showing you the functions that you would use. And the data, like if this was in Excel, in this data here, right here you go left click and drag, and then in parentheses, and that's what I mean by data. Okay. Now, suppose a histogram is desired to determine if the distribution is close to a normal distribution. Now, in this course, in this development, at this level, we're not actually trying to do a statistical test on if it's statistically significantly normally distributed. We're just saying I would just recommend, from a practical standpoint, if it's relatively symmetric, use the normal distribution. It's close enough. The decision was made to create a histogram with 5 intervals, and this 5 intervals was random, was arbitrary. Since the range is 374, because I just calculated up here, the width of the interval would be, if I divide that by 5, it's 74.8 approximately. So the range, it goes from the minimum of 351, the max of 725. So the range is 374. Divide that by 5 intervals, it's approximately 74.8 per interval. But I arbitrarily selected 76 and defined the intervals as presented below. In other words, 350 to this, because I wanted to start at 350, end at 730, and that's why I picked 76. It was a nice, two neat numbers to begin, which is below 351, above 725, I went all the way to 730. Okay, and so my interval is 76. Well, I take the average of each of these intervals. The average is the midpoint, and then I count the number of my data. Whoops, didn't mean to do that. I count how many numbers are in that interval. Okay, and you include the upper, okay, and you don't include the lower, okay, and you don't, it's between this. Let me do it this way, okay. You don't include the lower, you include the upper, you count, and those are the frequencies, or the count. Turn out to be 100. I divide through by 100 and I get probabilities. Now the reason I'm doing this is the actual data. And so what you do in Excel, you can plot the frequency, you can plot the probability. There's a frequency plot, there's a probability plot. All I'm showing you is nice and symmetric. It's nice and symmetric around some mean, whatever it is. Actually, the mean we calculate up here is 539.36. So it's nice and symmetric. And the variance is 6670 with a standard deviation of 81.67. Okay, and so all I'm showing you here is the frequency distribution and probability distribution is similar to the normal distribution as presented in the Excel plots below. Thus, the data are assumed to follow a normal. In practice, that's really all you need. You don't need statistical tests in practice. As long as it's relatively normal, it's not too skinny, it's not too fat, it's pretty much normally distributed, you're fine. Okay, so then we go on. Now, sometimes the demand values are only available in aggregate form as presented in Table 2 above. Okay, where's Table 2? In other words, sometimes this is all you're given. You're only given this. Now, I generated this to show that the histograms are relatively symmetric. But I generated this from all the data, the sample data. What if you didn't have the data? What if all you had was this table? How do you determine the mean and variance from a table like this? Okay, and this table is the numbers, but sometimes a table is given as a graph. Okay, sometimes it's an aggregate form, as in a histogram. The mean and variance need to be determined from the aggregate data. To determine the mean and variance from the group data, consider the relationships. Now I put this in a box for those of you who care or who want to deal with it. You can go through this. This is a derivation. But now we'll use these I'm not going to do it, but you can. But I will if you want to come and ask me, and I'll go through it with you. Use these relationships to determine the mean and variance using group data. The aggregate form in Table 2 is copied here in Table 3. Okay. In other words, what I did, I copied the lower, upper, and the midpoint values, frequency and probability. All of these were copied from Table 2 up here. I copied all of these right down here. I copied them. And there they are. Now I'm labeled the midpoint x. I'm labeling the probability p. So I'm taking the x times the p. That's all I'm doing. If I sum that, that turns out to be the mean. It's pretty easy to do. I take the x, I square it, and times the probability. I do that right here. I bring that number down. I subtract the mean squared, and that becomes my variance. I take the square root of that, and that'll be my standard deviation. So when you have a histogram, a distribution, you have a midpoint, and have a frequency or probability, that's all you need to determine the mean and variance. And with a mean and variance, then you can do your inventory theory, inventory control, and inventory management. Okay, that's Table 3. In Table 4 below, the mean and variance and standard deviations are compared between the sample data using all the values and the group data using the aggregated information, or the histogram. Okay. The differences are not considered significant for our purposes. In other words, the difference between 539.36 and 539.24, I would say that difference is not significant. It's not important. They're essentially the same numbers. If you're trying to forecast a mean demand and you're in the 500s, less than 1, 24 to 36 is 0.12, 12/100ths of 1 is not going to be significant. Okay, you get the point. And the variances are not that different. And the standard deviations, again, relatively identical. Therefore, this empirical demand will be represented as the D, with a G being general. G represents the general probability distribution. So I have a general using the sample data or a general using the group data. Now the reason I say general is because we really don't know what the mean, variance, and standard deviations are. We used all the data, but again, this is just sample data. And we use the group data, which is even less accurate. So when you aggregate data, you lose discrimination in the numbers. You lose information. Since the probability distribution has strong symmetric appearance, assume normality, now apply the empirical distribution to generate policies. In other words, you use it anyway. Okay. Now, consider the stochastic demand single period. Let's see exactly what the differences are. Here's our sample data. I go through the numbers. Here's the group data. I go through the numbers. And notice the differences down here is 654 versus 651. Again, not that big of a difference. Another common procedure from the distribution presented in Table 5 above, since the stockout level is 8%, so notice we have a stockout level up here of 8%. Since the stockout level is 8%, we know that that probability is a stockout level. Thus, the value of Q such that the probability of the demand greater than that Q is 8%, or the demand of D less than Q is 92%, or 90.92 or 92%. I'm using those the same. It can be seen in Table 5 as Q54. When you look up here in Table 5, we can see, where's Table 5? Here's 4. Oh, here it is in Table 5. Sorry. Table 5. So what I did here, I pulled down Table 5, okay, and here's my probabilities. Well, these are the probabilities. These are the same as the service level probabilities. Well, there's 0.92 right here. So I can say, okay, well, everything less than, here's my Q right here, let's say 654. In other words, these are my probabilities from my distribution. Now this Table 5 is just copied up here. Let me just show you. I'm copying it from Table 3, which was copied from Table 2. I'm just using this again. I'm just copying this down. So these are the probabilities within each of these bins or intervals. Okay, here's Table 3, Table 5. So now in Table 5, what I'm doing, I'm taking the probabilities right here, and I'm having the cumulative probability, or the probability of D less than Q. This is the probability between the lower and the upper. This is the probability less than the upper. Okay. Well, notice less than 92%. Well, that's going to be my service level, and so that's less than 654. So from the group data, I can say that 654 then, that's going to be the value less than that is going to be my service level, right? So I can determine my Z value, the value from my probabilities, which is going to be 654. A similar method can be done with the sample data. Rank order the demand data and select the 92nd value, which is the 92% of the total numbers. In other words, I took this data set up here. Let's come up here to the very beginning. Here's my data. I took all my data set here. I just sorted them. I rank ordered them from 1 to 100. Then over here I had an index that went 1 to 100. Now, if you have numbers that are more than 100 or less than 100 or not 100, in other words, what you do is you divide through by the total to get an index so that you have a scale from 1 to 100. Now notice the 92nd value then turns out to be 92% of my distribution is 650. So notice the value then of the 92nd number is 650. Now if the service level calculated does not exactly match the value in the column of Table 6 labeled service level, suppose if you divide by let's suppose the total number, instead of 100 up here, suppose you had 121 or something. Well, this may not be exactly 92%. But whatever number you have here, if you don't have it, then you can interpolate between the numbers. Like if you had a 91.8, 92.6, you interpolate to get 92 between these numbers. Notice that this is not an exact science, but it can significantly increase efficiency and lower cost. Okay, so this session is just some practical things on how, tricks of the trade on how you get it done. Well, the last thing we do is something called the base stock level, and this is periodic review. So in the periodic review, the base stock level, first let me illustrate what it is, okay, what the base stock level is. So this time we are not continuously reviewing our inventory as it's coming down. Here's our time, and here's our inventory here. This is this sawtooth curve, and we're assuming our demand is random, so it's not a straight line. It's going to be a wavy line because we have stochastic demand. Now we're coming down here. Let me just illustrate what this is. We're saying, okay, well, I'm going to review this every t time periods. In other words, right here, I'm reviewing it. It's periodic review. I'm going to wait for another t time periods, another t time, and that's going to be the next period, and then review it again. So you're not looking at the inventory all the time. You're doing it periodically. But when you do review it during time, you say, okay, what's my inventory position? Now that inventory position can be defined many different ways. To keep it simple, I'm saying my inventory position is how much inventory do I have? How much physical inventory do I have in my inventory? How many items do I have? Suppose I'm looking at my inventory, I have 100 items. Okay, I have 100 items, that's my inventory position. Now, in practice, the inventory position is more complicated than that. It could be, oh, your inventory position, this is how much you have in inventory. Here's how much you've ordered that is arriving. Here's how much is back ordered that will arrive. Here's how much your current orders, back orders. So this is how much that is accounted for. You subtract the spoilage. You subtract. So there's all different kinds of things that you can put into inventory position. That varies with application and company and industry. To keep it simple, we'll just say how much inventory do we have. Suppose our inventory position is 100 items, okay? And then we're going to calculate one number, and that is called the base stock level. I call it the base stock level. It's called different things. Suppose the base stock level that we calculate is 1,000 items. No, let's make it simpler. Let's say 1,000 items. That's our base stock level. Well, if our inventory position is 100 items, if our base stock level up here is 1,000 items, then what's the difference? 1,000 minus 100 is 900. That's my lot size. I order 900. So the periodic review system says every time, periodically, when you review your stochastic periodic review lot size, then every t time period you're going to order whatever your inventory position is from your base stock level. That's your lot size. So let's wait for t time. Let's suppose every week, every Friday we place an order. So this next Friday we're placing an order here. Oh, what's my inventory position here? Oh, my inventory position here is this Friday is 200. My base stock level is 1,000. I'm ordering 800. So I wait for a week. And next week, what's my inventory position? Oh, it's 150. Oh, my inventory position is 150. My base stock level is 1,000. Now how much do I order? Oh, I order 850. And so it's really simple to do, but the question is, what's the base stock level? Okay, with a stochastic demand periodic review system. Let's do it. So the base stock level is made up of the lot size plus the statistical safety stock. So the lot size, and here's where the interpretation of a base stock level periodic review system comes in. The lot size is going to be the T, your inventory period, plus the lead time times the mean. That's how much you're accounting for. So let's back up. Where does that come from? Well, when you place an order here, okay, you place an order. That order must satisfy not only the lead time, but also the inventory period before you receive the next, you need to account before you account for the next lot size that you order. In other words, how much time does that order have to satisfy? Well, it has to satisfy the inventory period, but it's also going to satisfy the next lead time. Because when you order this has to satisfy enough time until the next order has been considered. This order will consider this lead time in the next inventory period. But you have to have enough inventory to satisfy that lead time. Because It is not deterministic. It's stochastic. It's unknown. It's random. Okay, so there's your lot size. Now your statistical safety stock is the same. It's a z times sigma times the square root of t times the lead time. And so now your base stock level simply is t times your inventory period plus the lead time times the mean, plus the statistical safety stock, which is your z of alpha, which is your stockout level, the sigma of d, which is your demand from the demand. It's the standard deviation of your demand, of your the variability of your demand. It's the standard deviation. The square root of your inventory period plus your lead time. And so remember, to compare this, remember when we calculated the ROP, it would be, let me do this. Before the ROP, let me say ROP was the lead time times this, times z times sigma times the square root of the lead time. But with a base stock level, these, you add the inventory period in to get your base stock level. So the inventory policy is every t time periods order up to the base stock level from your inventory position, and that right there is your inventory policy. Do the calculations. Here's our demand rate, 539.6274. Inventory period is 1.5. Lead time is 0.2. Stockout level is 10%. From the stockout level, the service level is 90%. Our alpha, or z of alpha is 1.282 approximately. Here our base stock lot size is T plus LT. The base stock level then is this, the Q. The safety stock is T plus LT. I calculate that to be 137. I add those together and I get 1053. You can do the numbers. So the inventory policy is order up to 1053 every 1.5 weeks, because 1.5 weeks then is my inventory period. And there's your policy. Order up to 1053 every 1.5 weeks. Okay. Now finally, if we can also assume that not only the demand is normally distributed, the lead time also is normally distributed. So now the lead time is a random variable. So given the demand during lead time, by the way, I'm just going to mention this. We're not going to be using this that much, but this represents extensions. So the demand during lead time is the sum of the demand, where the lead time is random variable and the demand is random variable. So the lead time up here is in the summation. Okay, mean during lead time, then the expectation of this is a random variable, but this random variable has two random variables in it. One's a demand, one is in the sum. So the expectation of this expression, this random expression, stochastic expression, is the expectation of lead time times the expectation of demand. It's pretty straightforward. And I derived this in my videos. The variance of the demand during lead time here is a little bit different. And I derived this in my videos. And it turns out to be this expression. So the reorder point becomes this expression. I'm not going to go into it. I do go into it in my videos on my YouTube channel and my website. And there are the calculations. But one thing, and I won't even go through the calculations. But one thing I do want to say is, again, here you have deterministic demand. 108,809 is a policy. Here you have stochastic demand. 155,809 is a policy. The lot size does not increase. The ROP does. You order it sooner. You don't order more. The demand and lead time are stochastic. And what do? Do you order more? No, you order it sooner. The ROP increases, not the lot size. And that's really the basic takeaway, that you can, whether you go through the arithmetic and all the probabilities and the calculus and everything, whether you go through that or not, this concept, and you can have good, maybe not optimal, but good policies to run a company. Well, that's all I have for Inventory-2 lecture stochastic models. Between now and the next time I see you, I want to urge everyone to be safe and take care.